So my name is Majo Orozco. I'm a PhD student in the genetics department at Yale, and I'm the coordinator for the building blocks from atoms to anatomy talk. Today we will hear from three incredible people that have prepared super interesting presentations about what they're most passionate about, and hopefully you'll have a lot to learn and think about after today's talk. So to introduce the speakers, today we have Shashank. He is a PhD student in the astronomy department. His research focuses on how galaxies evolve and change throughout time. And a fun fact is that he loves to bake cheesecake, and I hope we get to try his cheesecake at some point. The next speaker is Aurora. She's a PhD student in the chemistry department. She studies how proteins fold, and she'll tell us all about proteins today. And a fun fact is that she loves to make pipe cleaner flowers. So it looks like Aurora is a crafty gal. And our third speaker of the day is Miranda. She's a PhD student in the Earth and Planetary Sciences department. She studies vertebrate paleontology, and she'll focus on that for her talk. And a fun fact of hers is that last year she spent 5 months hiking from Georgia to Maine on the Appalachian Trail. So very cool. Okay, so let's begin. Our talk is focused on building blocks. So I want you to think about Legos and how a beautiful and complex structure is built from hundreds, if not thousands of pieces, just like this green one over here. And if we zoom in into this green piece, we can see that it looks very simple at first, right? There's plastic that makes up these shapes that are able to bind to other shapes and make these really cool structures. However, have you ever wondered what makes up this building block? It might be looking something like this, and I'm sorry if I'm making you remember your high school chemistry figures and all these squiggles. But today I want you to get comfortable with the question of where does everything come from? Starting off, we'll have Shashank talk about these squiggles that I just presented and where those symbols come from. He'll talk about the chemical elements that some of us might have learned in high school and how the periodic table came to come about. Next up, we have Aurora, who will present the journey of how food and its building blocks are essential and how they help our body function. And finally, we will have Miranda, who will shed some light on the history of human construction and what the building blocks are, how we slowly but surely came to look human. Today, through these three talks, we will go on a journey of understanding what builds the universe, our bodies, and how in reality we are all connected. Building block over building block, we will lay the foundation of what we hope is a fascinating journey through the construction of life as we know it. I hope you enjoy and help me welcome our three amazing speakers. Take it away, Shashank.
All right, hi everyone. Give me a thumbs up, you can see my screen. Awesome. Hi, so my name is Shashank. I am a PhD student at Yale's astronomy department. Thank you all so much for coming here on this wonderful spring evening. So we probably remember this from high school chemistry, the good old times. This is the periodic table of elements. It's a list, a compilation of all of the elements that we know about that exist in nature. Right now, there are 118 different elements on the periodic table, and each one of them has a distinct chemical and physical signature. We probably can recognize some of these. We have oxygen, which is the most important gas in our atmosphere for us. We have carbon, which is found everywhere throughout our day-to-day lives, in our bodies, in our jewelry, etc. Calcium is a very important component of our skeleton. It makes up our bones. We have iron over here, which is used throughout our construction, and so much more. So if we want to quantify some of this, if we look at what is the average chemical composition of life on Earth, we can see it is mostly made up of carbon and oxygen. and hydrogen. And there are some amounts of other elements like calcium and phosphorus mixed in there. If we then go on to what is the average composition of Earth, it is pretty similar. We have a large portion of the Earth is made up of oxygen. There's also some amounts of silicon and aluminum in here. These are the building blocks of sand and rocks, which, of course, we know Earth is made up of. However, if we then go on, zoom out more, and then look at what is the entire universe made up of, we see a very different story. The universe is predominantly made up of hydrogen and helium, and everything else is all of the other elements only make up about 1%. So we are really on a very in a very special place in the universe on this little blue planet. So in this talk, I hope to address the question of how does nature make all of these different elements? Where do these elements come from? And in order to understand this, we need to now zoom in and look at the building blocks of matter itself, which are atoms. An atom consists of a nucleus, which is made up of protons and neutrons, and electrons, which are orbiting around this nucleus. We know that electrons are negatively charged, protons are positively charged, and neutrons have no charge. Now, a fundamental property of charges is that unlike charges attract, whereas like charges repel. So that means that an electron which is orbiting around the nucleus is going to be attracted to all of the protons in the nucleus. And this is how an electron stays together with the atom. This is very analogous to how the Earth goes around the sun due to gravity. However, that means that all of the protons, which are all smushed together within this nucleus, are going to be feeling a very strong repulsive force against each other. So how does the nucleus stay intact? Shouldn't these protons be feeling a very strong repulsive force, which would just rip the nucleus apart? And the answer to that is that there's another force which is even stronger than the electric force, and this is called the strong nuclear force. And this is the glue that holds a nucleus together and prevents it from being ripped apart. I'm not going to go into too many details about this strong nuclear force, but an analogy for this is that it's like a piece of Velcro. If the two straps of a Velcro are very close together, that is when they can stick together and it's hard to rip them apart. But if they are far apart, then they basically feel no force against, with each other at all. And the same thing for a nucleus. If you have all of the protons very close to each other, then they are held together by the strong nuclear force. However, far away, they're going to be feeling a repulsive force because protons are like charges, like protons, are going to repel each other. So the name of the game is that if we want to create a new element, we need to somehow overcome this repulsive force between atomic nuclei and bring them close enough together that the strong nuclear force can take over and finally merge them together. And in order to overcome this repulsive force, this requires extreme conditions. It requires very, very high temperatures and pressures that are not found anywhere in the universe except in very special conditions. And you probably have heard of the term nuclear fusion. This is one of the fundamental challenges in energy in our energy creation. And nuclear fusion involves trying to overcome this repulsive force. That's why it is so hard to have success in this. And something else I want to point out is if we consider light elements like helium, which only have a few protons in them, they only have a few protons, so the repulsive force amongst nuclei are going to be pretty small. However, heavier elements like iron and gold have a lot of protons, so it requires an even higher temperature and pressure in order to fuse them together to overcome this repulsive. So let's start right up at the top of the periodic table, which is hydrogen and helium, the two lightest elements in the universe. And they probably have the most exotic origin of them all. They were created all the way at the start of the universe in the Big Bang. In the early 20th century, the astronomer Edwin Hubble discovered that the universe is expanding. And that means that if we turn back the clocks, at very early times, the universe was much hotter and denser because matter can neither be created nor destroyed. So at very early times, the universe was very hot and dense, and this is the perfect conditions required for creating new elements. So we can say that at early times, the universe was like a pressure cooker, just churning out all of these new elements. And so hydrogen and helium was mostly created all the way at the start of the universe, the Big Bang. But what about all of these other 100 plus elements? Well, it turns out that some way or another, all of these elements were created in stars. So we need to now go on to understand what is a star. The closest star, of course, is the sun. A star's entire life is a battle between gravity and pressure. Because stars are so massive, they have an immense gravitational pull, and gravity wants to try to contract everything together, to bring everything close together. And this is balanced by by the internal force of pressure within a star. Where does this pressure come from? Well, that comes from within the core of a star where nuclear fusion is taking place. Stars are mostly made up of hydrogen, and when in the core of a star, when the temperature is millions of degrees, hydrogen atoms can be smashed together to form helium atoms, and in this process, they produce energy. And this is what we observe as starlight. So, as long as a star has enough fuel in the form of hydrogen, it can survive against gravity and maintain some sort of equilibrium. So low over here, we need to distinguish between low mass stars like our sun and high mass stars. First, let's go ahead with low mass stars. Low mass stars, as we just saw, give off light and energy by converting hydrogen into helium, just like our sun. But eventually, they're going to run out of hydrogen. That is when they enter the red giant phase. A red giant is a star which has run out of hydrogen, run out of fuel within its core, and so it's no longer fusing hydrogen into helium, but rather helium into other elements like carbon, nitrogen, and oxygen. And that is how red giants give off light. We can see a red giant tonight if we just look up in the sky. If we find the famous constellation of the Big Dipper and then trace the tail of the Big Dipper form along a straight line, we are going to see a very red star, bright red star, and this is Arcturus. Arcturus is a red giant star. It is more than 25 times the size of the sun, and it is one of the stars which have run out of hydrogen and are churning out all of these new elements. So these elements, like carbon, nitrogen, oxygen, and some amount of lithium, are formed within low mass stars. Now note that low mass stars can't form any of these other elements because they don't have the required temperature. Remember, if we want to form heavier elements, we need to overcome a larger repulsive force. So low mass stars just simply aren't hot enough for that. Eventually, a red giant is also going to completely run out of fuel, and that is when it's going to enter the planetary nebula phase. The planetary nebula have nothing to do with planets. When we first discovered them, we thought they were planets, so the name just stuck around. And this is when the outer layers of the star just continue to expand and expand. And planetary nebula are really some of the most beautiful structures that you'll ever see in astronomy. Like, just look at how gorgeous these are. And at the center of these planetary nebula, we can see this white, this very bright point, and this is the remaining core of a star, which is called a white dwarf. And this is what the life of a low mass star looks like. On the other hand, the life cycles of high mass stars look quite different. And when I mean high mass stars, I mean like stars which are about a few times more massive than the sun. They start out similar, so they are also initially fusing hydrogen into helium and giving off energy. However, once high mass stars run out of hydrogen, they become a red supergiant. And red supergiants have a very high temperatures, so they are able to fuse all of these heavier elements like oxygen, silicon, iron, so all of these heavier elements in the periodic table are formed within the cores of high mass stars. We can see a red supergiant tonight if we look towards the west. If we spot these three very bright stars in a line, this is the constellation of Orion, Orion's belt. And on the top left of Orion is a very red bright star named Betelgeuse. Betelgeuse is a red supergiant, and it is more than 700 times the size of our sun. So if our sun was replaced by Betelgeuse, then we would literally be swallowed alive by that red supergiant. However, Betelgeuse is not going to stick around for too long because eventually, once it completely runs out of fuel, it is going to explode in a massive explosion called a supernova. Supernova are some of the most violent explosions in the universe, and all of these elements that were created that were churned up within the core of a star are now suddenly flung out into space. So supernova are what release all of these heavier elements which are formed within stars. And they can also superheat the surrounding gas, forming new elements. So if any of you are wearing any jewelry that are made up of gold or silver, you are literally wearing something that was forged within a supernova, forged within one of the most violent explosions in the universe. Now, after a supernova, the remaining core of a star is going to contract and form either a neutron star or a black hole. I'm not going to talk too much about black holes in this talk. They are super fascinating, but neutron stars are some of the most exotic things in the universe. They are incredibly dense. Imagine if we took the entire sun and packed it within the size of New Haven. So a single teaspoon of neutron star material would weigh over about 10 million tons. And we think that there are millions of neutron stars that are just floating around in the Milky Way galaxy. So that means that eventually neutron stars are going to find each other and come crashing into each other, merging. And when neutron stars merge, they also give off some of the most violent explosions in the entire universe. And in this process of neutron star mergers, they also create new elements. We have observed some of these neutron star mergers. Back in 2017, we observed a neutron star merger, which was in another galaxy, about 1 billion trillion miles away. You can see over here how this explosion started and then eventually faded over time. And this neutron star merger created a tremendous amount of new elements like gold and silver and platinum. So in this explosion, there was enough gold to fill up tens of Earth-sized planets. Just imagine if we could get our hands in some of this gold, huh? That would make us very rich. So I'm going to end with showing the periodic table, but color coded by where all of these elements originate from. And we can see that all of these elements, well, at least most of these elements, originated in some or another from stars. So especially some of these elements that are really crucial for life ended up over here on this pale blue planet from stars. So I'll end with this quote by Carl Sagan. The cosmos is within us. We are literally made up of stardust. Thank you.
Thank you, Shashank. We have a few minutes for questions if anyone has anything that they would like to ask Shashank.
Are they putting their questions in the chat?
Yeah, they can write their questions in the chat or they can unmute themselves by raising their hand and I can unmute you.
Yeah, I see a question. Go ahead.
Can you hear me?
Yeah.
So in a neutron star merger, like the name would imply that neutron stars are mostly made of neutrons, but I remember you saying that when we're talking about elements, they're being formed of protons and electrons getting very close together.
Mhm.
When that happens, where are those constituent like protons and electrons coming from?
That's a great question. It turns out that protons and neutrons can actually transform into each other at very high energy. And you are absolutely correct. Neutron stars are mostly made up of neutrons. But when neutron stars crash into each other, there's so much energy released that sometimes these neutrons and protons can like transform into each other. And that is how we end up with new elements. This transformation between neutrons and protons doesn't ever occur on like the energies that we encounter in our day-to-day lives, but they can happen in these extreme astrophysical conditions. Yeah, great question.
Is it possible that the universe contains helium and hydrogen? It's just we haven't explored it yet.
Um, so you're asking if it contains more helium and hydrogen than we think?
Most. That's
Yeah,
what you said, right? You said the most most made up of helium and hydrogen. Is it because we haven't explored them? Because we have only, even by telescope, we have only seen very little of the universe yet.
Yeah, great question. So we actually have seen most of the universe. Like if we just go out and look at what our galaxy is made up of, what our stars made up of, our what the entire universe is made up of, we actually think we do understand this fairly well. And yeah, most of the universe is indeed made up of hydrogen and helium and everything else is just 1% of that, which is sometimes I can barely believe it. It's just a very mind-boggling fact. Yeah, you're absolutely correct.
We have a question in the chat. I can read it out for you. Um, did the gold or other heavy metals on Earth come from meteorites or from other original space dust that coalesced into planets?
Yeah, also great question. I do think uh the some amount of gold did indeed come from meteorites. But then we can ask where did that gold on the meteorite come from, right? So yeah, like I'm not exactly sure like how what percentage of gold from the earth like formed within the earth or like is on earth and then came from meteorites. But all of the gold in the universe, like if we consider the earth, other planets, meteorites, everything eventually did originate from some of these exotic things like neutron star mergers or from supernova. Let me go all the way to the very end here. Yeah, all of the gold did eventually originate from like either neutron star mergers or exploding supernova. Yeah.
Thank you, Shashank. There's other questions in the chat. Feel free to answer them as Aurora's setting up. I'm gonna change the spotlight now. There we go.
Yeah, should I like stop sharing that?
Yes, please.
Are people still asking questions or should I go ahead and start?
You can start.
Okay. Hi, everyone. I'm Aurora and I'm a second year grad student in the chemistry department. And today I'll be talking about protein digestion. And specifically, we'll be exploring what occurs to proteins when we eat an egg. So to build a house, you need a lot of different materials like brick, plywood, cement, nails, and what have you. And just like you need a lot of different materials or building blocks to build a house, building blocks to build organisms or humans like us. And similar to how you need different elements to make cement like calcium, iron, or aluminum, our body's building blocks also need different components or building blocks to build them as well. So as an example, to make humans, we need an organ system, but then to make those organ systems, we need organs. But then to make organs, we need tissues. And then to make those tissues, we need cells. But then to make those cells, we need organelles. And in the end, what kind of ties this all together is elements, which we excitedly just learned about today are made mostly from stars. So then those elements can sort of be connected together to form a molecule. And if those small molecules are then connected together to form even bigger molecules, they make up this macromolecule, which can then be used later on to make us in the future. And under this realm of macromolecules, there's sort of 4 categories, which today we'll only be focusing on proteins. But proteins, you might be wondering, why should I even care about this? Or why are they even important? Well, proteins have a lot of different functions. They, when we think about proteins, we might think about them in the context of health. So maybe before going to the gym, you eat protein powder to try to help you build muscle. But these guys are actually, they have a lot of different jobs. So they can work as enzymes to help speed up the buildup or breakdown of a different compound. They can also help carry small molecules around in our bodies. They can work as antibodies to help protect us from sickness, as well as a variety of different other functions. But now that I've talked about sort of why proteins are important and how they can be used to make humans, so as a building block, you might now be wondering what exactly even is a protein. A protein is made up of different amino acids, and an amino acid is made up of different elements like hydrogen, nitrogen, carbon, and oxygen, which again, we just learned how those are made today. And then when different amino acids are linked together through a peptide bond, they make this protein chain. And we can sort of think about these amino acids like letters in the alphabet. So depending how you arrange these letters or these amino acids, then you get different words, or in this case, different proteins. Now, proteins don't just exist in this straight line of amino acids. There's actually a hierarchy to how they fold. So when they're in this straight line, that's called the primary structure. And then when the elements in these different amino acids interact more, they form a higher ordered structure, which is called the secondary structure. And then those will interact even more to kind of fold into this straight shape, which is called the tertiary structure. And this tertiary structure is very, very important for the protein's function. So, but if there are a variety of different protein chains, then these can interact through the quaternary structure. And this hierarchy we can kind of think about in the form of friendship. So first, you might meet someone, form a connection, and be an acquaintance. So that would be kind of like your primary structure. And then as you spend more time and you interact, that would be kind of like your secondary structure. And as you form a closer relationship, that would be sort of like your tertiary structure. And then if a variety of different groups or friend groups meet together or interact, that would be sort of like your quaternary structure. Now, as I sort of alluded to, the 3D shape or the folding of a protein is very important. And this is because if a protein somehow misfolds or doesn't fold correctly, then that can be pretty detrimental to us because it is linked to different or a variety of different diseases like Alzheimer's or Parkinson's. So it's very important for us to make sure that our proteins are stable and properly folded. Now, how do we even get proteins in our body? Well, there's a variety of different food that are high in proteins, like cheese, lentil, and beans. And I really love eggs, even though they're pricey now. But for today, we'll be focusing on what happens to the proteins when we eat those eggs. So as a general overview, when we eat the egg, there is an enzyme, which I mentioned before, but those are proteins that help break up or build up different or like other proteins. So when we eat the egg, an enzyme comes and helps break down the protein chain into individual amino acids. And then our bodies are so smart that they can then use those individual amino acids to make new proteins for our body. So as kind of a general scheme, our bodies kind of help break down our food to form new components or repurpose those proteins or other macromolecules that we ate to help fuel our bodies by making new compounds. So now let's dive into the actual step of things. So here we have 3 steps, which occurs, or the first 2 occur in the esophagus and stomach. So in the first step, it's called mechanical digestion. And all this means is that when we eat the egg, we use our teeth to help break down the egg into smaller pieces. And then those smaller pieces will travel down through our esophagus into our stomach. And in the stomach, we might not think about it, but there is actually acid that will break down our folded protein into an unfolded protein, which is called denaturation. And as I mentioned before, the 3D shape of a function is the 3D shape of a protein is very important for its function. So when this happens, it makes the proteins that we ate lose its function. And if we kind of think or go back to the hierarchy of structure, it basically makes it go in reverse order. So instead of being folded in the tertiary structure, it'll go and unfold to reveal the primary structure. So then once this happens, there are new enzymes that come in and break down our protein chain into smaller chains of amino acids, which then travel down into our small intestine for the 3rd step. So in the 3rd step, our protein chain is now broken down into even smaller chains. And then these smaller chains will then be broken down into individual amino acids in the end. And then once that occurs, the individual amino acids can travel through our bloodstream and our body, depending on what we need, they can use it to make other proteins or store it as fat, as well as make other compounds that contain nitrogen, or if we really need it, our bodies can use it to make energy to fuel our bodies. Now, I've talked a lot about proteins and why they're important. But you might be wondering, how do we even know all this information? Well, there's a special type of protein called fluorescent proteins that are proteins that sort of glow. So when we attach this sort of glowing protein to some protein we want to study, we can take pretty pictures or images to try to figure out if they're localizing or congregating in a specific region of a cell, or if they're maybe interacting with other proteins. So we can basically just use this tool to kind of gather a lot of information to figure out how or what's important for this protein to fold or for the protein's function. And then later on, we can try to connect these sort of ideas to figure out maybe an antidote to alleviate some symptoms for diseases, or just to know a lot more about how proteins work. And hopefully, I've talked a lot about proteins, so hopefully I've convinced you that they're pretty cool. In my case, the sort of glowing protein I work with is red. And when I express and purify it, it looks sort of like strawberry milk. But with that, thank y'all for coming to my talk, and I'll be happy to answer any questions.
If you have any questions, feel free to write them in the chat or raise your hand and I can unmute you.
Are all protein sources pretty much the same for humans? I think so. I kind of only think about why does a protein fold the way it folds. I don't really think about the sources, but I think they do mainly come from just what we eat.
What are essential amino acids?
Essential amino acids, I think those are the amino acids that we really need to survive for the essential probably proteins that we need to function.
How do we get them?
I think we also get them from what we eat. I'm not really sure.
Thank you.
Mhm.
Well presented, both presenters.
Thank you.
So how do the proteins that like exist in humans compare to the proteins that exist in like other kinds of animals? Because I know you said that they get broken down. Do they get broken down because the proteins wouldn't be useful to humans in the form that we eat them? Or are they, or is it just like easier for the body that way?
I think, well, proteins are pretty delicate. So like with the acid, they can't, like no matter what, they'll unfold. But for your question on what difference, or like how are proteins different in us versus like other organisms, I think it's probably the size and then also the composition of those amino acids.
Thank you.
We have a question in the chat. I can read it out loud. Aura, thank you. Quantum computing is being built as having promise for predicting 3D structures of proteins for their amino acid sequence. Are scientists able to do that in any instances now?
Yeah, that reminds me of AlphaFold, which I think also predicts the structure of a protein based on the amino acid sequence. And I think those are pretty similar to the structure of proteins when people use other techniques like NMR or X-ray crystallography.
We have another question. I think you said misfolding proteins can cause diseases. Does that mean that we can cure diseases if we can fold them the right way again? Is that what you're looking at?
I think in this case, we're trying to prevent the protein from misfolding instead of trying to make it fold properly again.
Thank you. I think we can transition to Miranda's presentation now.
Hi, can everyone see my screen? Great. Well, hi everyone. My name is Miranda. I'm a PhD student in paleontology, and I study how animal skeletons evolve. And today I'm going to be talking about a really interesting skeleton, which is ours. So we just heard from Shashank and Aurora about atoms and proteins, which are building blocks on different scales. And I want to take us one step bigger and talk about building blocks that we can see, and that's anatomy. So within biology, there are many different scales that we can look at, and each one can tell us its own information about how life works. So anything from a cell to the ecosystem or the whole biosphere. But the scale that I'm really interested in, both in my PhD research and for this talk, is the scale of the organism. And that's because we are organisms, and I think we're the best equipped to understand this scale. So let's take a look at a couple of different organisms. Here we have a fish, a frog, a bird, and a human. And my big question for my PhD is, why do these animals look the way they do? And we can start by thinking about some of the building blocks that make up these skeletons. And these are all skeletons of vertebrates, which just means any animal with a spine. So they all have the spine as one building block. And in addition, they all have heads, and they all have limbs, so either fish fins or arms and legs. And these are the kind of building blocks that I'm going to be talking about today, and the ones that I'm really interested in my research. So you might be asking, why bones? And that's a really valid question because we know animals aren't just made of bones. And there's a good reason why we're looking just at skeletons, which is that they can be preserved as fossils. So this is a process of fossilization. When an animal dies, any animal, it has a chance of being buried, and then while the soft parts of the animal will rot or disintegrate away, the hard parts, so in this case the bones, will be buried under layers of dirt and rock and can be preserved that way in the exact place of death until they're eventually exposed by scientists. And this process can take thousands to millions of years, and so it can tell us a lot about life in the past. And in fact, looking at the whole fossil record can tell us a lot of information about the history of life. So the skeleton fossil record is about 550 million years old, and it also includes sites from all over the globe. So we have actually a huge amount of information. One thing that the fossil record can tell us is that organisms, be it plants, animals, bacteria, have evolved along with their environments throughout Earth's history. So in changing climates, changing continent structures, organisms have had to constantly adapt in order to survive. Another thing is that fossils can tell us about animal history, and that's because fossils are basically a snapshot of the animal right when it dies. So we can see not just what an animal looked like, but also when and where it lived, because that'll all be preserved right around the fossil. And to take that one step further, since animals are related by common ancestry, fossils can actually tell us a lot about our own history because our deep ancestors might be preserved as fossils, and then we can find out information about where we came from. So this brings me to one of the most interesting questions that paleontology can help to answer, which is, where does human anatomy come from? And to do this, I want to look at 3 different cases of specific parts of our bodies, which each illustrate a fundamental process in how evolution or macroevolution at this scale works. And so I want to be looking at the ancestral anatomy, so that's the bone structure or configuration of our deep, deep ancestor, and then look at human anatomy, and we can see how these are related to each other through transitional fossils, which show an intermediate state. So I want to start by taking you back to around 400 million years ago when most of life was in the water. And at this time, our ancestors were swimming around as some of these weird fishy things. And around this point, exactly 400 million years ago, was one of the most important events in the history of life, which is when animals conquered the land. So this is known as the water to land transition, and it really shaped life as we know it by allowing a whole range of new habitats for animals to live. So if we get down to the bones of the water to land transition, we can compare fish fins to the limbs of land animals like a mouse or a human, so our arms and legs. But without any further information, it's really hard to tell whether these things represent the same building block. Are they the same, or are they just completely different from each other? But luckily, fossils can help us to fill in this gap. And actually, the specific fossil that was able to do that was found in 2004, and it's called Tiktaalik. It's this guy on the left. And it's regarded as the missing link between fish fins and animal limbs because it's got sort of an intermediate anatomy that looks like a cross between fins and limbs. And since Tiktaalik, a couple other fossils have also been found to sort of flesh out this hypothesis that fins and limbs are actually the same building block. So this guy is Eusthenopteron, and it's a little bit fishier than Tiktaalik. So its fin over there looks a lot like a fish. You can see like the bones are really small at the base, and most of the fin is just soft tissues. And then we can also look at an animal that's maybe a little bit more similar to a land animal than Tiktaalik is. This one is Acanthostega. And that limb might look a little more familiar. It has fingers in purple, and it's looking more like an amphibian or a human or other land animal. So if we look at those two fins, limbs, and then we also look at Tiktaaliks, we can kind of see that each one of these colorful building blocks can be connected through this evolutionary transformation. And so this is an example of homology. Homology is when the same trait or the same building block can be identified in different animals. And so the example here is as you go from Eusthenopteron on the left to Tiktaalik in the middle to Acanthostega on the right, and these couple other fossils to fill in those gaps, you can really trace each building block and see how it contributes to the limb. So homology is really important for our understanding of modern diversity too. So if we look at building blocks of the limb or the arm in modern animals, we can also see this same pattern. So like one of the building blocks is the upper arm, which is in green for all of these. And then another building block might be the forearm in pink and orange. And then the wrist and the fingers could be the third building block in yellow. But in order to connect this to fish, we really need transitional fossils like Eusthenopteron that can explain how these are connected to anatomy that looks just really different. So in this case, we have the ancestral state is the fish fin, and then the transitional fossil is Tiktaalik and others like it that show the kind of intermediate form. And then finally, we get to land animal limbs like our arms. But now I want to take you to a completely different part of the body, which is our ears. And bones might not be the first thing you think of when you think of ears, but actually the three tiniest bones in our body are all part of the middle ear. So they look like this. They're called the hammer, the anvil, and the stirrup, and that's a photo of what they actually look like. Basically, the way that they work is they transmit vibrations from the eardrum to the nerves and eventually to our brain by vibrating. And these bones have a really unlikely origin, which is that they used to be part of the jaw in our ancestors. And so if we can trace this diagram of mammal evolution from the oldest at the bottom to the youngest at the top, you can see that over 100 million years, the jaw went from being a composite structure made up of a bunch of different bones to being really dominated by this one big bone. And having the big bone really being responsible for all of the jaw functions of eating, chewing, biting, that really freed up the back of the jaw, those three colored bones, to take on a new function, which in this case is hearing. And so the reason we know that this is what the evolutionary trajectory looks like is because of two really important fossils. This one's Thrinaxodon and this one's Morganucodon. And so you can see in the diagram, both of them have a transitional anatomy between the ancient composite jaw and the modern ear situation. These animals are around 200 million years old, and so overall this transformation took over 100 million years. It's very slow. So this is an example of an exaptation, which you might notice it sounds similar to adaptation, but it's when a trait is co-opted during evolution to serve a new function. So in this case, the trait or the building block is those bones at the back of the jaw, and they're being co-opted from an eating function to a hearing function. And we can get a little more in detail with this. So we've got a gecko on the top, which represents the ancestral configuration where all of the small bones are still part of the jaw and still part of the eating contraption. And so that's the red circle. Those bones are all being used for feeding. And then in the gecko, the only things that are being used for hearing are in the blue circle. That's the gray and orange bits. So that's the ancestral configuration, and it was the same in ancient mammal ancestors. But then if we move to the transitional fossil Morganucodon, you could see those circles start to overlap. And what that's telling us is that the bones that are in between the overlap, so the green and the dark blue bones, they're being used both for a feeding function and for a hearing function in the same animal. And that is a really cool way for us to think about how the transition might have happened, because obviously if you just go from having one function to having a different function, that might leave the transitional animal kind of helpless. But Morganucodon needs to be able to eat and it also needs to be able to hear. And if those bones are being used for both functions, then it's able to survive. And then finally at the bottom we have a modern mammal, which is an opossum. And you can see once again those red and blue circles are separate because only the one big bone of the jaw is being used for feeding and everything else is being used for hearing. So opossums probably are a lot better at hearing than something like Morganucodon. And this is what our ears look like as well. A really interesting thing that we've just learned from research that's coming out right now is that this situation might have actually happened multiple times within mammals. Once in the group that includes all the weird mammals like platypus, and then another time in the group that includes more normal mammals like a cat. And we know this because of a new fossil, Vilovolodon. And basically the idea is that for both lineages of mammals, the feeding function was mostly controlled by the one big bone. So the smaller bones in the back of the jaw were really free to take on whatever function was necessary. And it happened that the hearing function was necessary and was taken on by these bones in both mammals. So in this case, the ancestral condition is a composite jaw made of lots of bones. Then transitional fossils like Morganucodon, Thrinaxodon, Vilovolodon show us some of these intermediate steps to getting to what is the modern human middle ear bones. So now we know that the ears came from jaws, but where did jaws come from? And to get to the bottom of this, we have to look at sharks. Sharks are some of the oldest animals that are still alive today. They're basically living fossils. Sharks have been around even longer than trees have. But what I want you to notice about the shark is right here, which is the gills. And each of these gill slits is supported by a pair of bones, one on each side, and we think that one of those pairs of bones became our jaws. So this is how we think that happened. Basically, there would have been some animal like an A that had gills but no jaws. And then one of the pairs of gill arches would have gotten just a little bigger and a little more robust over time, over millions of years, to become a jaw. And then eventually that jaw gained teeth in a separate step and became what we think of as jaws today. And some evidence for this is that we still have animals alive today that have gills but no jaws. They're both really disgusting. The top one is a lamprey, which is known for swimming around in lakes and in the ocean and ripping chunks out of bigger fish with its disgusting jawless mouth. And the hagfish is known for being really slimy. But both of these guys, if you look right here, they have gills that look kind of like the shark gills, but neither of them have jaws. So this is pretty good evidence that gills are older than jaws. And we also have some fossil evidence for this. I think these fossil jawless fish are a lot cuter than the modern ones, but these are really, really diverse animals, and they all have gills but no jaws. So we go from an animal like a lamprey that has gills and no jaws to an animal like a shark that has both gills and jaws. But we're talking about human anatomy today, and humans have jaws, but we don't have any gills. So what's going on? So the human condition is an example of overprinting, which is when new evolutionary changes obscure inherited traits. So in this case, the inherited trait is the gills that are all behind the jaw, but in humans, that's been obscured, and they're only left as tiny little pieces of cartilage in our neck and in our jaws. Overprinting can make it really, really hard to understand evolution, but luckily we have another source of evidence besides the fossil record, and that's from embryos. So if you look at the shark embryo and the human embryo over here, we can see that they actually look a lot more similar than you might expect, even though a shark and a human look so different. So we can look at each of these embryos and we can see that these different colors, which are the gill arches, they seem to be the same building block in embryos. And as we watch the shark develop into an adult, we can see where those end up. They end up in the jaws and in the gill arches of the shark. But if we watch those same ridges in the human embryo as it develops, we can see where they end up in us. And that's small parts of our jaw cartilage and our throat cartilage. And I just learned this recently that some people have like a tiny hole near their ear, and that is a remnant of these developing ridges. So like the ridges in the embryo in the different shades of blue. And sometimes it will get left over as one becomes an adult. So these two things are really not so different after all. So in this case, the ancestral condition is gills. And then jawless fish, fossils, and embryology can help us figure out that those led to jaws. And then we have an animal like a shark that has jaws and gills, but then in humans, those gills behind the jaws are gone, leaving us just with these tiny little traces of what was there before. So I want to leave you with these three ideas. The actual terms are less important, but I think it's really cool to think about the types of processes that we can identify that happen during evolution. So the first is that the same trait can be identified in different animals. That's the building block. Traits can also be co-opted during evolution to serve new functions, so rearranging those building blocks in a new way. And then finally, newer evolutionary changes can obscure inherited traits, so the building isn't always linear. And I also want to leave you with these three examples of where some of our anatomy came from. So fish fins evolved to arms and legs, jaw bones to middle ear bones, and gills into jaws and tiny bits of cartilage in our neck. And so, like all life on Earth, we really are only what we are today because of those who came before us and because of our history. And throughout these three talks, we've been looking at nature's building blocks of different scales, from atoms to proteins to bones. And what we really want to leave you with today is the idea that we and the whole rest of our world around us, we're all made up of building blocks that can be put together in different combinations. Thank you.
Thank you, Miranda. If anyone has any questions, we have like a minute or two for you to put it in the chat or raise your hand and I can unmute you.
My question is, the only sea creature who is considered a mammal is the whale. Has any study been done on that as to how they developed vertebrae?
Yeah, so you're right. There are mammals that have gone back into the water, and it's not just whales. There's also seals, dolphins, a lot of things like that. And whales are actually like most closely related to other mammals that we know like to be in the water sometimes, like hippos. So that's probably how that happened, that they were animals that were running around on land and would occasionally go into the water, and then they started to do it more and more and more until eventually it became whales. I hope that answers your question.
Yes, thank you. Very good presentation.
I think we're right on time, but if anyone has any questions, feel free to put them in the chat and maybe we can stay here for a minute or two so Miranda can answer them. But thank you so much for coming. And I hope you enjoyed and learned about the building blocks that make life.
Absolutely. Thank you.
Thank you all for your presentations. Very interesting, and I'm very happy to have you. And thank you everybody who attended. Hoping to see you at some of our future programs.